Welcome to this explainer. Almost every website today offers those super convenient buttons: continue with Google, sign in with Apple, or log in with GitHub. Most of us click these buttons without a second thought, and a few seconds later, we're seamlessly logged in. No new username to invent, no new password to remember. It feels almost magical. But today, we're going to strip away that magic and unpack the complex, surprisingly elegant cryptography and protocols that actually make that button work behind the scenes.
Here is our roadmap for today. First, we'll look at the magic behind the button. Second, the authorization code flow. Third, authentication versus authorization. Fourth, unpacking the three tokens. And finally, defending the secure session. Let's get right into it.
Section 1. The magic behind the button. Let's demystify single sign-on. So, imagine you're logging into Spotify for the exact first time using Google. How in the world does Spotify know who you are without ever seeing your password? Does Google just secretly send it over? Can Spotify read your private emails? Answering this core security fear is absolutely crucial to understanding how modern delegated authentication actually works. To see how your credentials stay completely safe, let's meet the cast of characters in our login narrative. First, there's you, the user. Second, Spotify, the application you actually want to use. Third, Google, acting as both the identity provider and the authorization server. Fourth, we have Google's resource server. That's what physically stores your profile info. And fifth, lurking in the background, is the attacker. Now, it's vital to note here that the attacker's goal usually isn't to break the underlying cryptography. That's honestly just too hard. Their real goal is to steal tokens, trick the implementation, or impersonate you.
Moving right along to Section 2, the authorization code flow. Let's follow the journey of a login request.
The literal second you click that login button, Spotify doesn't ask for a password. No way. Instead, it builds an authorization request. This contains a client ID to identify itself and a redirect URI telling Google exactly where to send you back. Then it physically redirects your browser away from its site and over to Google. From there, you authenticate securely on Google's end, and because you're typing your password directly into Google, it's completely hidden from Spotify. Finally, Google verifies your identity and pops up a consent screen.
And this brilliantly illustrates a core OAuth concept called a scope. You know when that consent screen pops up and it asks for permission to view your basic profile and email? It is not asking for your password. These specific permissions are scopes, and they are strictly governed by the principle of least privilege, meaning applications should only request the access they genuinely need to function. So if Spotify just needs your name and email to create an account, it should absolutely not request a scope that grants access to read your entire Google Drive.
But happening completely out of sight is this tiny, mighty technical detail, the state parameter. Before redirecting you, Spotify generates this random value called state. When Google eventually sends you back, Spotify checks to make sure the return state matches the original one it created. This little detail validates the request and totally protects the flow against cross-site request forgery, or CSRF attacks. It literally protects millions of logins silently every single day.
So, once you click Allow on that consent screen, Google doesn't just send your sensitive data directly through your browser. That'd be way too risky. Instead, it sends a short-lived authorization code back to Spotify. Think of this code as just a temporary claim ticket. Spotify's backend server then takes this ticket and makes a highly secure server-to-server HTTPS request directly to Google's token endpoint to trade it in. The actual sensitive exchange for real tokens happens entirely between their backend servers, far, far away from your potentially vulnerable web browser.
To make this exchange even safer, modern implementations rely heavily on a security extension called PKCE. That stands for Proof Key for Code Exchange. This is especially vital for mobile apps and single-page applications. Think of PKCE like a secret handshake initiated by your specific browser. Even if an attacker somehow manages to intercept that temporary claim ticket, they don't know the handshake, so the ticket is totally useless. It guarantees the code only works for the exact application that requested it in the first place.
All right, Section 3, Authentication versus Authorization. Let's clarify the jargon. Now, developers often use these terms interchangeably, but they are very different. Let's look at the distinct concepts here. On the one hand, OpenID Connect, or OIDC, is like an ID badge. It handles authentication, literally verifying who you are. On the other hand, OAuth 2.0 is like a key. It handles authorization, determining what you are allowed to access. So in short, OIDC proves you are you, while OAuth opens the door.
Next up, Section 4, Unpacking the three tokens. These are the keys to the kingdom.
Spotify doesn't just get one master key from that server-to-server exchange we talked about. It typically receives 3 different tokens, each with a very specific job. First up is the access token. This is what Spotify uses to access Google's protected APIs to get your profile data. It's intentionally short-lived to minimize damage if it ever gets stolen. Second is the ID token, provided by OpenID Connect. This contains your actual identity information like your display name. And finally, the refresh token. This one is long-lived. Instead of making you log in every single hour, Spotify uses the refresh token to silently obtain new access tokens in the background. But because it lasts so long, this refresh token is highly sensitive and has to be fiercely protected.
So the crucial point here is, how does Spotify actually know the ID token isn't fake? Well, Spotify doesn't just blindly trust the data it receives. The ID token is digitally signed by Google. Spotify uses digital signature verification to cryptographically prove that the token genuinely came from Google and hasn't been modified by some attacker in transit. Pretty clever, right?
Which brings us to Section 5, Defending the Secure Session. Let's see what happens after the handshake.
After successfully verifying Google's cryptographic signature, Spotify drops Google out of the equation entirely and creates its own authenticated user session. This is key. Spotify doesn't have to keep asking Google every few seconds if you're still logged in. Once that initial trust is securely established, Spotify takes over completely and manages your session from that point forward.
Let's shift to the attacker's perspective for a second. Since breaking HTTPS or Google's digital signatures literally just isn't practical, hackers target specific implementation flaws instead. They'll build fake OAuth consent pages to phish you, or they'll register malicious apps that request super broad permissions, just hoping you won't read the scopes before clicking allow. They also hunt for poorly stored refresh tokens on infected devices, look for misconfigured redirect URIs, or target applications that lazily bypass those required signature checks we just talked about.
So, stepping back from all the cryptography and network requests, here is the core takeaway of this explainer. Dismantling the biggest myth on the web. Google never, ever sends your password to third-party applications. Instead, it issues cryptographically protected tokens after successful authentication and user consent. The application only receives the exact information and permissions you've explicitly approved. No more, no less.
Strong protocols like OAuth 2.0 and OpenID Connect provide an incredible foundation, but it's the correct implementation that actually provides the security. So I'll leave you with a provocative thought. Where is the vulnerability in the next app you authorize? The next time you click Continue with Google, I highly urge you to actively review those consent screens and really look at the scopes you're granting. Keep learning, stay secure, and thank you so much for joining this explainer.